There's a lot of talk about artificial intelligence these days. Artificial intelligence this, artificial intelligence that. But what I find most interesting about AI, no one ever talks about. It's that we have no idea why they work as well as they do. I'm not talking about what's sometimes called the black box problem, which is that no one really knows why an AI comes to this or that conclusion. You feed it data, ask it a question, and it gives an answer, but it can't explain why that answer makes sense, and sometimes not. It's like a teenager, but without the eye rolling. Somewhat dated but illustrative example of the black box problem was the AI tasked to figure out which patients who presented in an emergency department were at risk of pneumonia. It found that people with asthma were at particularly low risk. The reason, it turned out, was that in the training sample, the people who presented with asthma and symptoms of pneumonia were admitted to intensive care right away, while others received delayed treatment leading to worse outcomes. It's for reasons like this that we'd like to know why a model came to this or that conclusion. We don't trust black boxes, and indeed there are many efforts to make AI explain its reasoning. But this is not the problem that I'm talking about today. I'm also not talking about the problem of badly specified goals that can lead to unintended outcomes, like a recent study by researchers from the University of Oxford who asked an AI to minimize the number of crashes in a train network. The AI concluded quite reasonably that you can't crash a train that never leaves the station, so it just stopped all trains. Genius. This is a more funny than scary example of a misalignment problem in which the human intention was not well coded. But this is also not what I'm talking about today. Instead, I'm talking about the curious question of why the currently most widely used AIs don't just fit all their many parameters to the training data and are then unable to make further predictions. This problem is known as overfitting, and the dirty little secret of AI is that overfitting doesn't happen as much as expected, and no one knows why. A simple example of overfitting is this. Say you have 4 data points and you fit a 5th-order polynomial to it. What's the prediction you get for the next data point? It could be anything, because the 5th-order polynomial has more free parameters than you need to fit the 4 points to begin with. It's a general problem you have with any sort of model. The more freedom there is in the model, the more parameters, the better you can fit it to the data you have, and the more ambiguous the predictions become. Now, the current large language models and other AIs that we are using are all based on what's called a deep neural net. These are basically big sets of numbers called weights that are adjusted during the training so that when you later enter a query that was not in the training data, the neural net can match that to an existing pattern and give a right answer. The currently largest neural nets have several hundred billion up to 1 trillion or so parameters. The funny thing is now that the neural nets don't overfit even if they could. You see, with any model, you have to reach a balance between how well you can fit each individual data point and how sensitive you are to these points. If you're very sensitive to each point, then you're overfitting and will not fit new data well. Let's suppose that the horizontal axis here shows how big the error of the model is on new data, and the vertical axis shows, loosely speaking, the number of parameters, so the complexity of the model, if you wish. A simple model is very robust but can't fit the data well. Now, if you increase the number of parameters, then the performance increases because you can fit the data better. There's a sweet spot, and after that you fit all the data that you have, but new data isn't fit well. This is overfitting. The weird thing is now that with neural nets, if you just keep on increasing the number of parameters, the curve goes down again. This has been dubbed the double descent in a 2019 paper. Why does that happen? No one knows. The speculation that makes most sense to me is that models don't overfit when they could because the overfit isn't stable under something that happens during the training runs. They almost always default on a fit that's dominated by as few relevant parameters as possible and then fine-tune with the remaining parameters. But it's unclear whether that's correct. I find this a very interesting problem because I think it'll tell us something about how the human brain works or how complexity arises in general. I also think it might be a good idea to figure out how the software works that we're handing the world over to, but maybe that's just me. I was very surprised last week to see Elon Musk tweeting about neutrinos. Yes, neutrinos, particle physics. Anything that potentially challenges the standard model is a very interesting experiment, he writes. What's he going on about? And is it correct? Let's have a look. Hello. Hi, Elon. You're building a supercomputer. Well, that's very nice. A name for it. All right, let's see. We have X, the X prize, X space. How about expensive? Bytezilla. Yeah, that's brilliant. Go for it, I say. I have to work. Love you too. Bye. So, about those neutrinos. Neutrinos are a type of elementary particle in the standard model of particle physics. The interesting thing about them is that we know there's something wrong with them, but we don't know what. Neutrinos are, as the name suggests, electrically neutral. Because they have no electric charge, they interact very rarely and are hard to measure. But they have been measured, and one of the things that physicists have found out about them is that the three types of neutrinos can change into each other. They oscillate, as physicists say. The thing is now that for this neutrino morphing, the oscillation to be possible, neutrinos need to have masses. We've known this for about 20 years, that neutrinos have masses, and there's been a Nobel Prize for that. We've also known for about 20 years that calling neutrinos ghostly will not win you a Nobel Prize in literature, so you can stop doing it. You have probably heard that particles get masses from the Higgs field, and that's correct. But you don't just need the Higgs field. You need two versions of the particle for the Higgs mechanism to work. You need what we call a left-handed and a right-handed version. They are mirror copies of each other, but they do behave differently, so we can tell them apart. All massive particles with spin 1/2, besides the neutrinos, for example the electron and the quarks, have left-handed and right-handed versions. If you combine those with the Higgs, you get masses. But for neutrinos, we've only ever observed the left-handed version. And with only the left-handed version, we can't use the Higgs field to give them masses. Yet they do have masses. So how does that work? Physicists have come up with 3 different ideas for giving neutrinos masses. The fascinating thing is that all of them require some new type of particle. So we know that the particles that we have measured so far are not it. There's got to be more. The first option is to postulate that right-handed neutrinos exist. We just haven't yet observed them because they're too heavy. In this case, neutrinos would get masses like all the other particles. And yes, the right-handed neutrinos could make up dark matter. The second option is that neutrinos are different from all the other particles, and that their left-handed version is the same as the right-handed one. This is called a Majorana particle. If that was so, you could then just take 2 of these Majorana neutrinos and get masses from the Higgs field. If neutrinos were Majorana particles, that would allow for a particular type of radioactive decay of neutrons known as the neutrino-less double beta decay. And that brings me to Elon's tweet. In his tweet, he's mentioning an experiment called Majorana that was looking for this neutrinoless double beta decay. This experiment didn't find anything and was discontinued a few years ago, so God only knows why Musk is mentioning this now. But there are a few other experiments still looking for this decay. For example, the Cuore experiment at Gran Sasso in Italy or Panda X in China. Majorana particles, by the way, are named after Ettore Majorana, who came up with this neutrino idea and then disappeared at the age of 32 and was never seen again. Ghostly indeed. Okay, so we have right-handed neutrinos or left-handed being the same as right-handed. You can combine these two, in which case the right-handed neutrinos are too heavy to be produced at the next bigger particle collider. And then there's the third option that no one ever talks about, but which I personally find most interesting. It's that you create a mass from the left-handed neutrinos and the Higgs without making the Majorana by coupling it to a pair of Higgses. The reason no one ever talks about this is that it creates a mathematical problem in the standard model. The standard model would then break down at high energies, but this might just mean that at these high energies there has to be a new particle popping up. So in this case too, there has to be something new. That said, while we know there has to be something new, we don't know where to find it. This is why every time an experiment that looks for some rare decay or a new particle and doesn't find anything, that's not called a negative result. That's an interesting bound on new physics, and they say they need to build a bigger detector. If you remember, I joked recently that my phone is really a particle detector that's searching for telephoning gravitinos that are candidates for dark matter. My phone detector hasn't delivered negative results. Oh no, it's delivered interesting bounds on new physics. As some of you pointed out entirely correctly, this just means I need a bigger detector, so here we go. Hey everyone, welcome back to our science news. Today we're diving into a hot topic. Bill Gates recently got fired on social media for claiming that planting trees can't save us from climate change. Is he right? Let's have a look, starting with just exactly what he said.
I don't plant trees.
There's a lot of people who are very enamored with trees. We've got trees on this stage. Some people would even say that if you just planted enough trees, it could take care of the climate issue altogether.
And that's complete nonsense.
Okay.
I mean, are we the science people or are we the idiots? Which one do we want to be?
The ex-Twitter fallout wasn't nice. You are the idiot, Bill. Bill deserves to be in prison. Why does anyone listen to this evil man? And one guy used the opportunity to proclaim that Gates is wrong and to promote his tree planting company. I'll admit that I'm one of those people who are very enamored by trees. They're really good listeners, and if they get too boring, you can chop them down and heat with them. That said, it makes sense to think that trees can help us fight against climate change. Trees absorb carbon dioxide, use photosynthesis to split it up, store the carbon and release the oxygen. The carbon goes into trunks, branches, leaves and roots, and over the course of time, some of it gets deposited into the soil. So let's just plant trees then and solve all our problems. Indeed, in 2019, a paper appeared in Science magazine saying that we could basically fix climate change if we just plant trees everywhere there's space. The authors estimated that this would require about 1 trillion trees, covering an area approximately the size of China. That, so the estimate, would remove about 700 billion tons of carbon dioxide from the atmosphere. Removing that much carbon dioxide would keep us within the Paris goals if we reached net zero by 2050. This is why some people have enthusiastically said that planting trees has a mind-blowing potential and that forest restoration is overwhelmingly more powerful than all of the other climate change solutions proposed. The paper even gave rise to the 1 Trillion Trees campaign, whose goal is, what the name says, to plant 1 trillion trees to save the world, basically. It's a nice story. Unfortunately, it turned out that the estimate in the 2019 paper was wildly over-optimistic. It was criticized almost as fast as it appeared for overestimating how much land would be available for planting trees and how much carbon the trees would eventually remove. The corrected estimate is about a fifth of that in the original paper. One also has to keep in mind that trees don't grow on the snap of a finger. It takes decades for them to grow, not all of them survive, and who will do all that planting anyway? Science eventually published a correction to the study, and the lead author, Thomas Crowther, said somewhat exasperated that he never said we should plant 1 trillion trees. I get the feeling that he and his co-authors didn't quite anticipate how much attention the paper would attract, and I wasn't even doing science news then. Now you might say that, well, even if the estimate was a factor 5 too high, that'd still be something like 20% of what we need to remove. And yes, that'd be pretty good, but that'd require that we plant trees in basically every corner where there aren't already growing trees, and the trees actually grow there. But good soil and tree-friendly climates aren't easy to find, and if you find them, people would rather use them to grow food. There's also the issue, as another study has found, that if you plant trees on formerly barren land, then that significantly changes the reflectivity or the albedo of the surface. As a consequence, Earth retains more heat. According to some estimates, that could effectively counteract the carbon dioxide removal by 30%. Indeed, another study found that if limiting temperature increases our goal, we'd be better off plastering land with solar panels than planting trees. Okay, you might say maybe trees won't fix climate change, but trees are good for other things, right? Like parks are good for your mental health. Trees are known to keep cities cooler, improve air quality, and planting things ought to be good for biodiversity too. Well, it's partly right. Monocultures generally aren't good for biodiversity, so you have to be careful with what you plant. But sure, trees are good company. However, if you listen to the Gates quote in context, it's entirely clear that he wasn't dissing trees in general. He wasn't even talking about climate change in general. He was specifically talking about the potential of planting trees for offsetting carbon dioxide emissions. It was a reply after the interviewer asked Gates about his involvement with the carbon removal company Climeworks. Listen yourself.
But are you offsetting your own personal emissions
Yes.
with that? And can you give us a sense of the scale of that?
It's like 10 million a year.
Okay.
Peanuts.
And just
It's
to be
a variety of things. The Climeworks is part of it. You know, buying electric heat pumps for low-income housing where they get the benefits of lower monthly bills, and I take the carbon credits for those things. You know, there's solar panels. There's a huge variety of things. I don't use some of the less proven approaches.
Such as?
I don't plant trees.
And that makes a lot of sense, not just because of the butchered estimate for the potential of carbon dioxide removal by planting trees, but also because a lot of carbon offset projects that relied on reforestation turned out to have prettified their numbers. At least at the moment, you can't trust carbon offsetting with tree planting, and it makes a lot of sense that Gates spends his peanuts on more reliable approaches. So is Gates right? Science says yes, and keep on dusting those solar panels. Yes, climate change has some benefits. There'll be fewer skiing accidents, for example. But seriously, it's true, not all consequences of climate change are bad. And I'm all for full disclosure, so today I want to talk about what's good about climate change. Let's have a look. When we talk about climate change, we often focus on the increase of the global average temperature. But a global average temperature isn't any more real than global average cheese. Though American cheese comes pretty close, reality is more complicated. The impact of climate change that we feel is regional, and this is where things get difficult because different regions of the planet are affected by climate change in different ways, and the change might not be totally bad. For example, the Sahel region of Africa is currently incredibly dry. Not much grows there, but climate models predict a significant increase in rainfall there, as much as 50% more and as soon as 2040. This should make the area more welcoming for plants and wildlife, and with that also for humans. Another good thing about climate change is that the northern regions warm particularly quickly and become more hospitable. This will benefit in particular Russia and Canada. A similar beneficial trend is already happening in some highlands where regions that were previously just too cold for agriculture can now be used. For example, in the highlands in central Madagascar, rice yield is projected to go up by at least 10%. Similar consequences will likely help growing crops in the highlands in Rwanda and Kenya. There are other benefits to climate change. For example, while we can expect more people to suffer and die from heat stroke, fewer will freeze to death in the winter. There are also a whole bunch of autoimmune diseases that flare up when temperatures drop, and the affected people probably won't mind a fewer cold days. Then there's the Arctic passage between the Atlantic and Pacific Oceans that might soon be ice-free year-round. That'd make it easier to transport goods along that route. And who knows, if you live in central London, your house might suddenly become beach property. So yes, climate change has some benefits in some regions, but in many regions of the planet, the climate zone shift will make it harder for crops to grow because it'll be too dry or too wet or too hot. Yes, plants like carbon dioxide, and higher carbon dioxide does benefit some plants, especially rice and wheat, but carbon dioxide isn't the only thing plants need to grow. If it's too hot or too cold or too dry or too wet or there's new diseases, carbon dioxide won't save the day. In this figure, you see projections from the OECD for the impact of climate change on agriculture by 2050. So you see more rice in Europe, more wheat in Japan, but overall it doesn't look good. Though I'm somewhat unhappy with this graphic because I don't trust numbers without error bars. In any case, the major problem with climate change is that it forces billions of people to adapt quickly. If you need to build new houses inland because your coastlines are eroding, how much money do you have left for breeding new crops? And if one country suffers, then all its trading partners will also suffer. This recent paper has a good summary of the expected income changes from climate change by 2050. As you can see, the further north, the better off you are, but not like Europe and the United States will remain unaffected. Basically, the need to adapt to climate change quickly pulls down the entire world economy, and there are very few regions in the world that will benefit so much as to make up for the global recession caused by this. But it's interesting to compare this new projection with a similar one from 10 years ago, in which the damage chart looked like this. As you can see, the major difference is Europe, which in the earlier projection was largely unaffected, but that's no longer the case. This is because the newer study took into account data about the actual impact we have seen in the past 10 years, and in Europe the temperatures have increased particularly quickly. The brief summary is, yes, climate change is good if you live in Siberia. So keep on dusting those solar panels, guys. Thanks for watching. See you tomorrow.